Okay, so as I was saying, welcome everyone to this new NEASQC webinar. I say new because we had some of you maybe attended the series of webinars we had more than a year ago. So I'm Pascal Bernier-Brunel. I'm the dissemination manager of the NEASQC project. I work for Eviden, and I'll be your host today. So before I hand over to the speakers, I would like to explain very quickly the objective of this webinar series. So our objective is to help the quantum community discover and test the libraries and tools we make available, and get your feedback. That's a second objective. And we are going to have monthly webinars until the end of the project, so until more or less end 2024. The full program is already available on our website, so please feel free to go there and check it. It will be updated very regularly. But I can already announce the next webinar, the October one. This one will be about quantum computing and CO2 capture. And registration is open. So if you go to our website, you'll have the registration link. Maybe I'll put it in the chat later. And then in November, we'll have a webinar about quantum probabilistic safety assessment. So here the date is already set, and we'll have in December, we'll talk about benchmarking, in January, financial applications, and then we'll have quantum natural language processing, measurement optimizations. All of our use cases will have at least one webinar. So today's speakers, you see, they are here with us already. So first of all, the technical director of our project, Cyril Alouche, has very kindly agreed to give us a small introduction today, since it's the first webinar of this new series. So he will explain what the project is about. Cyril is the head of quantum computing R&D at Eviden, that you maybe better know as Atos. We're changing names. It's a long story. It's not the topic. It's not today's topic, but it's the same company. And our main speaker today will be Arseny Kovyrshin from AstraZeneca, who will talk about a use case. Arseny received his PhD in quantum chemistry at the University of Münster, and he then worked at ETH Zurich, and he is now with AstraZeneca and contributing to NEASQC. So thank you, Arseny, for accepting to do this webinar, to share your research. So agenda, very simple, small introduction by Cyril, and then Arseny has the floor, and we'll take all your questions at the end of the webinar. I just wanted to mention some resources, additional resources that you may be interested in. They were already mentioned on the webinar webpage. We have two scientific publications that are related to today's topic, and there is also an open source library. And more generally, I really invite you to consult the NEASQC website and the use cases pages, because on each use case page, you have a list of publications and deliverables and open source resources available. So really, it's a good way to know what we have available. So sorry, no, it's not question time. It's Arseny time. So it's Cyril's time, sorry. So Cyril, can you share your slides and explain us a little bit about NEASQC?
Sure.
Excellent.
So, talking about NEASQC, so first you may notice the pronunciation. It's NEASQC for an obvious play on word. It stands for Next Application of Quantum Computing. It's part of the European Quantum Flagship effort. It's the first project that was funded by the flagship on software and application. So we started 3 years ago now, and still 1 year to go. And the principle of this consortium is that it's a balanced consortium between companies and academia. It really targets at real applications. We'll see in the next slide what kind of applications, and really you can see on the logos that it is quite balanced between let's say large and small companies and the academic world. And really the principle of NEASQ is that for we have 9 use cases, and for each use case we have a pair of an academic and an industrial that are working toward the demonstration of a quantum advantage on these use cases. These use cases have been both endorsed by the industry and the academia as feasible and that could reach a quantum advantage. So yeah, the symbols of our partners. And so really all 4 objectives that we are driving now for 3 years is first, of course, to explore these industrial use cases. That's, as I said, I repeat, really unique in the, let's say, in the quantum galaxy to have really such a project targeted at use cases and really demonstration of these use cases. There is also a software part indeed there, but all is aligned on the use cases. So another key objective is then to develop some open source libraries dedicated there also to real application, to practical application, in particular in the industry. We'll detail how you can benefit of these libraries and how you could even contribute. Also, an important part, and it is also the reason why we are doing these seminars, is to really to build a community around industrial applications. So we put a huge effort on dissemination, and Pascal is our dissemination leader, to really connect people who are interested in these applications, so that we can share knowledge and we can build first a community, but also the proper tools, meaning open source libraries. What I forgot to mention is that the libraries we are developing at NEASQ are copyleft. They are under the EUPL, the European open source license. So with no retain of property. And then our last objective is to develop the software stacks and also the proper benchmarks for these applications, and in particular to support the hardware platform that are developed by the quantum flagship. This part relies partly on the Eviden free framework called MyQLM that you can download, and a specific build will be adapted from this MyQLM to support both the quantum flagship platform and also the libraries that all the partners are developing for this. These use cases have been grouped into 3 main areas. The first one, of course, to which this seminar is devoted, is chemistry. So we have 2 use cases there. The first one, as Pascal mentioned, is the topic of the next seminar, which is CO2 capture. The reference industrial is Total Energy. The second one is drug discovery, and it is handled by AstraZeneca, and so Arseny is contributing to this one. Then we have another big topic, which is machine learning, quantum machine learning, and also combinatorial optimization. We have these 4 use cases. I won't dig into details. And then a last one about symbolic AI. algorithms for graph. And I repeat what Pascal mentioned. For each of these use cases, we will have a dedicated webinar. We offer public resources, for sure. One of the key objectives of NEASQ is really to help build this community and help also delineate areas for quantum advantage in the industry. So we have plenty of resources, all are managed by Pascal. We have our website on which you can find, in fact, all of them. You can follow us on Twitter, on LinkedIn. Even more important, of course, we follow, as all European projects, we follow an open science strategy. And so all our publications are in open access, and you can access them on Zenodo. And these libraries I mentioned, you can find them on GitHub. Currently, there are 9 of them, and our partners are continuously contributing, and some new one may emerge. And of course, we will disclose that on the social media. Then I'm done. Can hand over to Arseny.
Thank you very much, Cyril, for introducing this webinar. Arseny, the floor is yours. Are you ready to share?
Yes, thank you. Just a moment. I'll. Do you see my screen?
Yeah, full screen. Perfect. Thank you.
Great. Hello, everybody. Welcome to my talk on NEO approach on quantum computers. I'm very happy to present you this work we've done at the group of Anders Bro at AstraZeneca Mölndal. We've done this work in collaboration with IBM Research Europe and Harty Center SciTech based in Dursbury. And we are very grateful for funding received through the NEASQC project, as well as VACT program of Wallenberg Center for Quantum Technology. And let's dive into the project. So usually quantum chemistry relies on 2 foundational simplifying assumptions. The first one is that the electrons in proton can be described separately due to their huge mass difference. This is also known as a Born-Oppenheimer approximation. And the second one can go even further and claim that atomic nuclei behave as the classical particles, which means that they come into the Hamiltonian as classical point charges, basically. This is a great assumption. This is a great theory in general. But sometimes the quantum effect on nuclei can have considerable values and change physics considerably. For example, light atoms' nuclear quantum effects can make things like delocalization and tunneling and enzymatic catalysis, totemic transitions. Also, they can be really important for determining the stability of crystal polymorphs. The other aspects are the isotope dependence in reaction rates, also the electron-proton coupled charge transfer in the photochemistry. And of course, there's a lot of ad hoc approaches in quantum chemistry to deal with such situations. They all are great and very interesting and actually prove to be very useful. But they lead to quite complicated computational aspects. And there is a nuclear electron orbital approach. This approach was done in group with Schoenham Schiffer in 2002. And this stands as a compromise between the Born-Oppenheimer and non-Born-Oppenheimer approaches. Specifically, you expand your wave function as a linear expansion of products of electronic and nuclear wave functions, antisymmetric slightly determinant, I mean here. Of course, one not only limited to the fermionic nucleus, but also to the bosonic one. But in general, nuclear electronic orbital approach uses and treats quantum only light nucleus, such as the protons or the deuterium atoms, etc. similar. So let's dive into the Hamiltonian. What does it mean for chemistry in general and for our physics? So if you, on this screen, you see the Hamiltonian second quantized representation. So the terms in blue, they are traditional electronic structure terms, and the terms in red, it's those which comes from the new theory. Specifically, those are nuclear kinetic energy, nuclear Coulomb interaction, electron-nuclear Coulomb interaction, as well as classical nuclear Coulomb interaction. So those terms we had to implement additionally into the quantum computing framework in order to capture all the effects I mentioned before. So in order to have such Hamiltonian, we have to also implement certain algebra for our creation and annihilation operators for electrons and for the nuclear as well. For example, we still have to obey the fermionic anti-commutation relations. Additionally, we have to introduce commutation relation between distinguishable particles, be that bosons or fermions. And also one can have the treat the bosonic particles with the direct or compound boson mappings. For the distinguishable particles, we use just direct Hilbert spaces of two different particles, which basically does a job to retain this commutation relations. So, of course, then one have to think about how to actually parameterize this wave function on the quantum computer. And for that, we have two very well-known parameterization, such as hardware efficient ansatz and unity coupled clusters. If for hardware efficient ansatz, everything is quite simple, you can take it out of the box and plug into your VQE routine you like, and start optimization of parameters right away. Of course, you can specify that some of the parameters will be ascribed to the electrons, some to the nucleus, and some to the electron nucleus. But in general, it's not important to treat them separately. And if you have a pretty good mapping for those, one can really get kind of good approximation for your energy, for your wave function. But of course, one knows that this hardware efficient ansatz has problems in the convergence, and also such problems as a lack of proper non-stochastic consideration scheme for the parameters. But also advantages of very, very short circuit depths. For the unity coupled clusters, one can say that's excellent expressive power. It's natural for quantum chemistry due to the unitary nature of the operators it has, but unfortunately it has quite deep circuits. And for the implementation, we also had to do and introduce additional excitation operators for the nuclear subspace and for the electron nuclear particles as well. Having this at hand, we can just continue further. And although we've got the wave function parameterization, we also need to introduce efficient fermion qubit mapping. For our system, we used mostly just electrons and protons. We just took traditional 2-qubit reduction schemes and expanded that to the 4-qubit reduction scheme, because we have additionally basically the subspace for the alpha and beta protons. Then, of course, one have to and can also introduce a spin projection for them, because usually if one treats this hydrogen molecule in quantum chemistry, one is interested in the ortho-hydrogen state, which is 75% in our atmosphere usually. And this is a triplet state for the protons. And basically, you don't need to treat a beta or alpha spin states, so you can basically reduce them. And additionally, one can also apply the reduction due to the system's point group symmetry. And in this table, you can see that if you gradually apply all those tricks, you can drastically decrease the number of qubits, like from the in the current basis set I'm specifying here, you can go from 16 qubits to 8 qubits. And if you check the number of 2-qubit gates, it's the same. It's quite good reduction in them. Also, the advantage is that you also at the end use way less Pauli strings in the Hamiltonian, so there are way less things to measure in the UVQE approach, for example. And this is quite so far also all very good. And if you try to optimize the energy, So with unity coupled cluster singles double ansatz, you can get very close to the reference energy. But for the hardware efficient ansatz, you still have a trouble. So it's like it's really not that efficient in optimization and in convergence. What the problem is in the initialization of parameters for the hardware efficient ansatz. But if one can think, maybe one can initiate it with the Born-Oppenheimer parameters. With those, where we get them just from the electronic structure theory. And in fact, can we do this? Presumably, yes, we can try that. And for the hardware efficient ansatz, one have to be a bit careful. One have to limit ourselves to the just control Z entanglement gates, and one have to be careful not breaking the particle and spin symmetries while introduction this new electronic parameters and initialization of the nuclear and the nuclear electronic parameters. While for unity coupled clusters, it's quite trivial. You just have to plug in electronic parameters and nullify all the rest. So what we get if we use such approach, then we can quite good approximate already with the two local ansatz the reference energy, which I think for the two local is very good. Of course, there is an advantage also for the unity coupled clusters, but as you see, you don't see that in the absolute energy scales, but you will see it when you check the convergence. The convergence is basically decreases a lot here, especially if you go to the higher dimensional parameterization schemes. Like if you add triples, then it's just more than 3 times shorter. So this is all very useful for the NEASQC devices and very good to have in general. At this slide here, I will just show that I indeed capture the entanglement between protonic and electronic parts of the wave function, and I don't really just introduce them without any purpose. So, for example, here I described the extension, sort of approximate setup for the extension of the hydrogen bond. I must say that here the separation is not really bond lengths between two bond lengths, but it is distance between the centers where I put orbitals, nuclear orbitals. It's a bit an artificial construct, but it can give you the qualitative understanding how entanglement changes while the separation of the two protons. And at the equilibrium distance, one got quite low entanglement, then it rises upon dissociation in the middle of dissociation and saturates at the dissociation limit, basically. And yes, indeed, we capture the entanglement between electrons and protons, and we are quite happy with this setup so far. So, but can we actually apply that for something else? Maybe we need to do some more complicated molecules. H2 and deuterium-2 is quite boring, right? For that, we really it wasn't hard to search for. I took just very notorious example on malonaldehyde. This is was vastly tested in the NEO framework in the NEO community. But for the quantum computing, I think it's interesting to introduce this for physicists and chemists. And here we try to evaluate the tunneling barrier, the barrier for the transfer of the proton from the left side of the this double well potential to the right side. So basically, for non-chemists, I maybe need to introduce some more information about the system. Malonaldehyde, this is a prototypical system to study the the tunneling of the hydrogen through the double well potential. So this, in our setup, we treated all the nucleus, including these 3 hydrogen classically, but this hydrogen, which forms bonds with these 2 oxygens, we treated that quantum. And usually there is a CS ground state corresponding to the CS point group symmetry, which means that the proton is located on the left or right side, And there's a transition state where the hydrogen is located at the middle, the center. And basically, if you evaluate the energy between a difference energy between this CS and C2V states, C2V state is a transition state, then you can evaluate the barrier of this double L potential. If you try to do that with Born-Oppenheimer approximation, then your estimate will be quite high. But let's try to do that with the non-Born-Oppenheimer, with the new approach. So in order to set up the Hamiltonian, we need to choose active space. Because we are quite limited in computational power, so we decided to use quite modest active space for the electrons. So here in blue and red, those are electronic orbitals used for setting up Hamiltonian, and purple and orange, those are protonic orbitals. So having enhanced such active spaces with the methodology I showed before, using the unity coupled clusters, singles, doubles, and triples, we managed to relate direction this tunneling barrier, which is quite close to all references we found in the web, in the scientific community, and it way closer than the traditional Born-Oppenheimer evaluation, which really overestimates it by 70% or so. We were quite happy about that we could capture such important physics, but can we do something else? Can we try to really introduce the dynamics into the system? For that, maybe one can mimic such a dynamics by trying to propagate and make those CI coefficients in our neurons, I mean this C mu nu, and make them time dependent and propagate them in time in general by solving and using this full CI equation of motion, where this H matrix is determined by the couplings between different electronic nuclear states. So in order to propagate them, there's some difficulties. So if you set up, for example, this Hamiltonian where the proton on the left, and even if you give them to the proton possibility to for the transfer to the right side and to the middle, if you apply this Hamiltonian and try to base the propagation on the Hamiltonian, nothing will happen if you start with the ground state, because you just will stay there forever, and this wouldn't be interesting. Instead, we need to introduce some setup, like we take a big stick and try to poke the proton and to just transfer to the other side. Maybe it sounds a bit crude, but there is actually quite good reasoning behind that. I can just mention it further. For example, let's try to do that by setting up several Hamiltonians, where we have exactly the same active space for the protons. It's like explained, like shown here. So this is a left active space, and here the protonic orbitals are all the same for the middle and same for the right. But take a look at the electronic orbitals. For the left, middle, and right, they are all different. They all were optimized by the SAF procedure, where we specifically locate our proton on the left for this setup, on the middle and on the right. There we get a certain polarization for the electron cloud, which actually adapt to the position of the proton. And then we can just make a linear expansion of those three Hamiltonians, and this will give us the time-dependent Hamiltonian, which we use for study of the proton transfer. For example, how can one understand that? It's like, imagine you have three different potentials. For the left potential, middle potential, and the right potential. And this potential confines the proton on the left, middle, and right sides. If you apply the left potential and try to sort of transfer the proton, it won't go, because it just goes through this side of the left potential. It tried to get out there. Maybe it just reached the middle state, but it won't sit there forever. So it will basically oscillate somewhere near the left equilibrium position. In the same way, if you apply right one, then you got this oscillation between the left sorry, if you apply the middle potential, then you got this oscillation between left location and right location, but it won't get, it will never reach the ground state, because applying this middle potential, we just introduce a resonance between the left and right locations, and protons start moving there. Instead, we want to have proton going from the left ground state to the middle and then to the right ground state. We must introduce some adiabatic transfer here. So basically, if you want to know how this alpha, beta, and gamma will change, then the best way would be to show this graph here. So we got really slow linear change in the alpha, beta, and gamma. And then in the next slides, I will show that it really leads to the adiabatic transfer of the proton from the left side to the right, just by changing this every time changing the alpha, beta, and gamma coefficients. But of course, this is not that simple, because if we have time-independent Hamiltonian, we cannot usually set up a usual propagator based on the constant Hamiltonian. Instead, we have to use like Dyson series. It's also a time-ordered exponential series. But in general, if the commutation, the commutator between those three Hamiltonians are not that high in value, maybe one can have a very low order approximation, like first order Suzuki approximation for the time order exponentials, like written here on the bottom of the slide. And as a circuit, it will look as follows. And having such a setup, such a propagator for our system, we can try introducing such a dynamics. Here I show you two regimes of our dynamics. It's the first adiabatic one, or slow, I call it, or non-adiabatic one, or fast. So if you see if you want to observe how does the energy, how does actually this compound Hamiltonian and its corresponding energy changes over time, you can check this graphs on the bottom, where we measure the corresponding energy for the left, right, and the middle Hamiltonians. So one can see that for the left Hamiltonian, energy goes up. So here it saturates and gets equal to the energy of the right Hamiltonian, because they're basically having the same. So they're symmetric basically, and then at the end of simulation it goes to the top. So basically there is no longer equilibrium state for the left Hamiltonian. In the meantime, for the middle one, it reaches at the middle of the simulation the ground state, the state which corresponds to the transition state, C2V symmetry, and then at the end it again goes up to some excited state. But if you take the right state, you see that it gradually decreases and reaches plateau at the middle. And then it goes again to the ground state, which corresponds to the location of the proton on the right side of the malonaldehyde. So if one want to see really, does our proton change the state, does it change the location, then it's cool to check the protonic occupations. And indeed, it does change the state, it does change the orbitals, and it goes from the left to the middle, and then goes to the right side. The same is for the middle occupation, for the right occupation. So one can be a bit more critical and say, but it's just orbitals, you don't know where they're located. But in general, in our setup, we just knew where the position, if you take the expectation value of the position operator, this would correspond to exactly positions on the left, middle, and the right. One, of course, can also plot the density, but I didn't manage to plot it for this presentation. I will probably do it further in the project. One can also want to know whether actually there's something happens in the electronic part, and indeed it happens. One sees that there is a sort of the electronic occupation changes and reaches some point in the middle where it's completely different from the beginning, and it goes to the same occupation as at the sort of at the end of the simulation. So I have to notify you that here actually I use to check our results the reference was integrator based on the Runge-Kutta first order approximation. And this dashed black lines, this is actually our reference results. And you see that our results based on the quantum computing or Zoid simulator, but this first order Suzuki approximation for time ordered exponents, they kind of agree very good with the Runge-Kutta first order integrator. So the last I want to mention is the fidelity. So this is like how close our system gets to the left ground state, middle ground state, and the right ground state. So absolutely the same pattern as for the protons. So we really, with the first order Suzuki Trotter scheme, we managed to get quite accurate results. So here, it was so far for adiabatics, for the adiabatic transition. Let's do it a little bit faster. Let's do it like twice faster and see how it goes. You see that the states are not that pure at the end of the optimization, and we got a lot of wiggles. So those wiggles are ascribed to the instantaneous transition to the electronic excited states and probably protonic excited states at every time we do propagation, which is like basically what happens when you do some process faster than adiabatic. Also, I must mention that here we also did better resolution, lower step for each propagation. And one sees that there is a number of figures for the occupations. They really decrease a lot. So here's like basically was the noise which we got from the pure resolution. But the thing is, still it's kind of big number for quantum machine, and now one can only dream about that. But one can show that it's in general possible once we have fully tolerant, full error tolerant machine. So the same about the fidelity. So one sees that it's not that close anymore to the transition state and to the ground state, and we got also a lot of figures which are ascribed to this instantaneous transition to the excited states. But here we got also little one, but we can get rid of them if we do it fully adiabatic. If we do it 5 times slower, then I read it, it goes quite smooth and very elegant. So there's no any wiggles except for the electronic occupations, but those comes through this pure resolution, because we here use the same resolution as before. So far so good, but what about the entanglement between the electronic and protonic part? At this slide you're going to see this, so it's quite interesting. So in principle, for adiabatic setup, there's a similar pattern between transition from left to the middle and from middle to the right, where the entanglement through the propagation rises to its maxima, where maximum correspond to the halfway transition to the middle, then it goes down to the reference entanglement for the transition state, and then again goes to the up and then down again to the original entanglement value for the electrons and protons. Of course, because we don't do it fully adiabatic, there is some wiggles here, and maybe this final value is a bit different, especially if we take into account the Suzuki Trotter first order approximation. We are a little bit off here, but we can get rid of that by introducing better resolution, smaller Suzuki time step, like is shown on photon-adiabatic transition. The reference is totally agree with our simulations, and also by decreasing the speed of transition. So the key message on this slide is that difference between adiabatic and non-adiabatic transition. So if in an adiabatic case we fully recover the original wave function at the end, for the non-adiabatic case we start actually acquiring entanglement, like we increase entanglement over our transition, and at the end our state is in some different excited state, and where we entanglement our electronic and protonic wave functions. So, so if you take into account that for a adiabatic transition, you can easily do it with VQE, optimization and protocols. For an adiabatic one need to go to the phase estimation based on the propagators of Suzuki order first order, Suzuki Trotter first order. And here, this slide, I show that, okay, if you do it 5 times slower, we really can for the references that we really can capture initial state, and it goes quite smooth. Although, because our simulation for Suzuki Trotter first order was way larger, we acquired a little bit more noise, but still I would consider this kind of stable integrator, and one can use it even for the long-term simulations. So, and that was our setup for making dynamics. As I said, it could be understood as maybe a bit cheating, but come on, there's no cheating in science. We just try to tweak a bit the system, and we don't really brutally change its potentials and try to like poke the transfer. You can imagine that our malonaldehyde is subjected to the ultra-fast laser pulses, like in the picosecond mode, and the first thing what actually interacts with those pulses are electronic clouds, so the electronic orbitals. And those electronic orbitals got polarized, and they try to then compensate it by moving our proton in space. And such a setup basically can be approximation or like reasoning of our simulation. And yeah, so to conclude all, I would say that we managed to introduce quite efficient and beneficial qubit mapping. Then we tested the Born-Oppenheim parameter transfer, which lowers final energy for the hardware efficient ansatz and for increases conversions for the unity couple clusters. Also, we proved that we can capture actually the quantum effects, and I would say it's in the second quantization, it would be first realistic quantum computing setup for the proton tunneling in malonaldehyde. And yeah, thank you for your attention.
Thank you, Arseny. Thank you for sharing your research with all of us. So now it's question time. So I will share my screen again.
Yep.
If I can.
I probably need to stop sharing, right?
No.
All good?
I'm the host, so I can stop you. I can do everything.
Very good. Very good.
Okay, so it's question time. You can ask your questions either in the chat in writing if you prefer, or you can raise your hand and we'll take your questions in turn. So while we wait for the first question, I would like to mention that the slides will be emailed to all attendees after the webinar, so you will get the slides. Also, this webinar was recorded and the recording will be uploaded to our YouTube channel. Actually, all of our webinars are recorded and you can find the recordings in our YouTube channel. So while we wait for questions, I had a first one for you, Arseny. What's next? I mean, what's next? Either in NEASQC, but maybe also beyond that for AstraZeneca.
Mm-hmm. Yeah, we are thinking about, so far it was like really a toy model. I think we need to increase the realism of this model, and what would be important is to introduce dynamics of the scaffold, of the classical scaffold. Maybe we have to introduce the changing scaffold of the molecule, and it has to also affect a lot the transition and the proton transfer in general. Also, probably we need to introduce some of the embedding schemes in order to have effects of the weakly interacting sites of the big proteins, for example, or similar things. Also, maybe one need to introduce some little bit more flexible and better representation for the nuclear and electronic orbitals as well. So far, it was all based on the Gaussian orbitals. They are not optimal, but it was like a proof of the concept, so to say.
Okay, so still a lot to do.
Absolutely.
I guess, yeah. That's what we hear from all of our use cases in NEASQ, really. I mean, we are advancing. I mean, research is progressing, but there's still a lot to do. So, okay. So any questions? I don't see any question coming in. Anyone wants to raise their hand and ask their questions? No? You can also ask questions about NEASQ in general. I mean, Cyril is here. He can answer, or in some cases, I can answer, not on the scientific aspects, but no questions? Everything was crystal clear? Okay.
I hope I didn't bother you too much. Sorry.
No, you were crystal clear. That's how you should take it.
Okay.
Cyril, did you want to have a last word in this webinar? Cyril, are you here?
Yeah. Can you hear me?
Okay.
Well, as I said, the most important in our project is to bring people together, even if they're not official partners of the project. So any proposal of collaboration or maybe just knowledge sharing is welcome. Huh?
Yeah. Yeah, and feel free to get back to us after the webinar. I mean, there is a contact point in the webinar invitation, so it will come to me. I can transmit whatever you send me. So don't hesitate to get back to us. And we have a contact form as well on our website. Well, I'm sorry there are no questions. It's a bit disappointing, but that's how it is. So. Thank you again, Arseny, for sharing this with us today. Thank you, Cyril, for being here for the first of our new series of webinars. And I hope to see you all on the 3rd of October for our second webinar, which will be dedicated to quantum computing and CO2 capture. Thanks a lot for being with us today. Bye-bye.
Thank you very much. Bye.
Thank you. Bye.
Bye-bye.
Bye.